And thank you very much for the opportunity to present our work. So this is a work on a functional renormalization group approach to quantum spin glasses. It's based on a work with Vincent Lauch and Dean Usman Samari. So the talk is structured as follows. So first I will give you a preliminary introduction about the methods and the model that we look at. Then in section 2 and 3, I give you the details of the methods that we use to construct our renormalization flow equations. Then in part 4, I will give you some fast results, quick results of each different method and how we interpret it. And at the very first section, we give a brief comparison with another slightly different model that we discussed in our previous studies and how it is similar to the model that we looked at in the main part. So for the preliminary part to start with, so first of all, what are spin glasses? So these are very well-known disordered models for a particle on a high-dimensional sphere. And in general, one interesting fact about them is that they go through a phase transition in low temperature that moves them to a glassy phase. And in this glassy phase, the system would experience a lot of metastable states, which basically trap the system in each one of them for a very long time. And also the number of these metastable states scales exponentially with the number of dimensions. So if we have very high dimensional sphere, so you can imagine there is a very rugged landscape that the particle has to move around and it gets stuck in each one of them for long times. And that's actually one of the reasons that it has many applications in machine learning and computer science and so on. And another fact about this glassy phase is that it has something that we call replica symmetry breaking. So later I will explain what is replica symmetry and what we mean when we say that this replica symmetry is broken. But it is basically you can imagine it as some sort of indicator for this glassy phase that we talk about. So more formally, okay, I think I jumped. Okay, so more formally, we can start with the classical action. So this is n-dimensional field theory on a one-dimensional space. And the action is given as these three terms. So the first and last term are very familiar. So this is one derivative term, derivative of the field in the kinetic sense, and then the potential, which is just some quartic potential, because as you remember, I mentioned that glassy systems are on high dimensional spheres. So we relax this spherical condition by introducing this potential that basically constrain the length of x squared. And then we have the main part, which is the disorder, indicated by the coupling of the field to this P tensor J. So this is a random tensor with Gaussian entries. So each entry is a Gaussian centered random variable. And the covariance of the entries is given by equation 3. And as you can see, there's this lambda, which is basically the strength of the disorder that we talk about. And there is this factor of n to the power of p minus 1, which basically takes care of the fact that we require the energy to be extensive for our model.
And x squared is nothing?
No, x squared is just a random, x squared is just the length of the, so x.
X is vector.
So x is a vector and x squared is dot product of, so it's the length squared basically. And then we introduce our partition function, which is the path integral measure. So dx in brackets is the path integral measure, and it's the path integral of the exponential of the classical action plus some coupling to plus the coupling to some source that we introduced by L. Here, just standard quantum field theory procedure. And then we do weak rotation going going to the imaginary time. So we indicate the weak rotated partition function as ZE, and its logarithm is the free energy that we looked at. And the free energy has this property that it is self-averaging. So in large n limit, it is basically concentrated around its mean, which we indicate by this bar. So whenever we have bar, we mean averaging over the disorder J. But still, it is a bit difficult to evaluate the average over the logarithm of a function. And what we do instead of that is introducing this replica trick, which we write the logarithm of z as limit of n to 0 of z to the power of n minus 1 over n. And as a result of that, we have this object that we focus on in the next parts, which is the z to the power n and average over j, which we call the replicated partition function. This replicated partition function has this property that, again, after it is basically constructed, you can imagine as having n copies of the system and then writing the partition function of it and then integrating over the disorder J. And if we do this whole procedure, what we arrive at is this path integral that we have there. So it's a path integral over each single replica. And then we have this modified action S tilde, and plus, again, the coupling of the field from each single replica to some source again. And if we look at this replicated action, so the exponential part that we get, we see that we have, again, the first and third part, which are pretty standard terms. So we have we have in the first term the sum over copies of the kinetic term, the derivative term in the kinetic term, and then we have also the sum over the copies of the potential. But there is a term coming from integrating over the disorder J, which was the second term in our previous action, and this term is basically coupling different replica with each other at different times. So this term basically, notably, breaks the locality that we have in our original action, and also couples the replicas with each other. And then we have this power of p, which in our case, so we focus on the case p equal to 3, so just 3 tensor disorder. So this means that this term gives us a bilocal sextic interaction, and for that we need to develop our own Feynman diagram machinery in order to be able to handle this. And so here we do this as an example for quartic bilocal interactions, but it's easily generalizable to sextic bilocal. So here we introduce these bubbles. So each of these bubbles represent one time and replica index. And as you can see, they always come together. So we don't need to separate them. So one bubble can represent the replica and time at the same time. And each dot means a field insertion. And the solid lines between the dots mean that we construct the inner dot product between the two of them. And then we need to introduce our Bayer propagator. So our Bayer propagator is given by 1 over omega squared plus mu1.
X alpha and beta, so some set of vectors.
So X alpha, X is basically an n-dimensional vector, and alpha is the replica index. So it says which vector from which replica. So from replica alpha, we have this vector X at the time t.
So it's 2. This summation alpha beta.
So yeah, there is 2 summations. So we sum over both of them. And there's also 2 integrals. So you see there is this implicit correspondence between time and replica indices. So we sum over both replica indices and we integrate over both times. Then we have our Bayer propagator. Our Bayer propagator is totally diagonal, and we have this we have it as a dotted line. And then the next natural question that we have to pose is what is the how the diagrams, given diagrams, scales with n, because we are going to n large limit. And we do that by so if we have a given diagram, for instance here, so we count the number of 4 vertices. So we have 1 here and 1 here and 1 here. So there is 3. So we don't have any in this example. We don't have any sextic vertex. But if we have, then it is -2. So it gives a factor of 1 over n squared. And then there is this term that there is this f, which means basically the number of closed faces. So if we have something like this red loop that you can see here, so we call it a face if we have a solid dotted line and they make a loop. So if it's a loop, it gives a factor of n, and if it doesn't make a loop like this blue one, it doesn't give any factor of n. And just to give you an example, in the quartic bilocal theory, the self-energy diagram, one-loop diagrams, are given by these 4 diagrams naively. But you will notice that these 2, so the second and the fourth, don't have any closed faces. So it means that they are 1 factor of n below the first one and the third one, which means that we only need to take the first one and third one into account. So next is our method that we are using, which is functional renormalization group. So in functional renormalization group, our aim is to interpolate basically from the microscopic action to the macroscopic action. So we start at some UV limit, and then we want to construct the effective action in the IR limit, in the infrared limit. And we do that by integrating out high momenta modes step by step. And in order to do that, we introduce this basically mass term to low momenta modes of our theory. So it gives this weight Rk, and then we integrate out the high momenta. And then you can imagine, so the Rk needs to fulfill certain requirements, but usually it can be shown that as long as these requirements are fulfilled, the theory is free of the choice of the regulator. In our case, what we did, we looked at Rk of p squared equal to k squared minus p squared theta k squared minus p squared. And you can imagine again, so below some threshold, it gives some mass to the theory, and then above that, it's the mass that is here. And then after that, we build this regulated partition function zk, which basically for a generic Lagrangian, it's equal to addition of these regulator term to the Lagrangian, and then do the path integral as usual. And then after we have the regulated partition function, what we do, we take the logarithm, we build the regulated free energy, and then we do the Legendre transformation of that regulated free energy, and this introduces us this gamma k effective average action. And this effective average action is exactly what we need to bridge between our microscopic action at the ultraviolet limit to the effective action at the infrared limit. And formally, the flow equation, the way that our couplings and our effective action flows from UV to IR is given by the Wetterich equation. And I think it would be best to understand it diagrammatically. So so there is this parameter t that we call the renormalization time, and you can understand it as minus the logarithm of k. And then there is this solid ball that you can understand it as the average effective action. So the derivative of the average effective action is equal to 1/2. And here we have this cross, which is the insertion of the derivative of the regulator. And then there is this solid line, which is the full propagator or effective propagator as 1 over gamma 2 plus rk, where gamma 2 is the second derivative of gamma k. And then the fact that it makes a loop means that we integrate over and we trace over basically the momenta. And so this is for just one momenta, but we have in our theory also the replica index that we have to take care of. But you can imagine we also do trace over the indices. It goes similarly. Before we move to the next section, the main problem with the Wetterich equation is that it is a nonlinear functional differential equation, and it is almost impossible to solve it exactly. And what people usually do is that they build approximation as some ansatz, and then they put the ansatz in the Wetterich equation. They interpret it. They interpret the results. Then, according to the interpretation, they modify the ansatz, and then they repeat it until they get some reasonable results, which is what we are exactly going to do. So, to give you a general way of how we approximate and truncate, so this average effective action, we can write it as a power series over the powers of the field. So there could be some factor 1 over n factorial, but we can always include it, absorb it by the gamma n. So in our case, we truncate naively in the first step after the sextic interaction, because our classical action is sextic, and we assume in the first step that our effective average action respects the symmetries that we have in our microscopic action. So because of that, we look only up to sextic interactions. So the 2-point vertex, effective vertex from this theory, we write it as a completely local symmetric term. So we have a momentum conservation factor, and then there is the ON symmetric matrix here, and then we have the effective mass plus the momentum squared. And the same goes for the 4-point interaction. So we omit the 3-point interaction because we assume that we have this ON symmetry that we had in our microscopic action. Then we go to the 4-point interaction. The 4-point interaction has again the same structure. So we have some momentum conservation, some tensor this time that respects the ON symmetry of the original theory, a coupling constant that we call U4, and 1/n renormalization so that it doesn't blow up in n large n limit. But it is a bit different with the sextic interaction because, again, if you remember, our sextic interaction was, we had a bilocal sextic interaction. So again, with the sextic interaction, we assume that we have a local interaction which has, again, the same structure as 4-point and 2-point interaction, which is some coupling constant and momentum conservation and ON symmetric tensor. But there is also another non-local or bilocal term, which is a bit different. So here we have, again, U6 tilde as that we introduce as the non-local coupling constant. But this factor that takes care of the symmetries in the term is a bit different. So again, we have the same ON symmetric tensor here, but the frequencies, the conservation of frequencies is a bit different. So it splits in two, which comes from the fact that our theory is bilocal from the beginning. So, and if we look at it diagrammatically, it means that we have a term like this, that that is the bilocal. That is the bilocal interaction, 6-point interaction. So if we look at one loop. So here in this perturbative method, we assume that our coupling constants are small. And if we look at the one loop diagrams that contribute to the U4, U6, and U6 tilde, we will see that we get these equations from the Wetterich equation. So the U4 contribution comes from one local sextic interaction, one bilocal sextic interaction, and two quartic local interaction. And the U6 dot, so the flow of the U6 comes from one contribution with local and one contribution with non-local sextic interaction of the quartic interaction. And then in the next step, we move to dimensionless coupling constants. So the bar means that we remove the mass dimensions that we have. So if we remove the mass dimensions, we see that we have this set of closed flow equations that we can solve. But before we do that, I would like to introduce, I showed the results at the very end, but before we do that, I introduce another approach that we use. So before I move on, please notice that here the propagators that we insert are bare propagators, not the full propagators. Sorry. So next we move to a more generalized non-perturbative approximation. So this is very similar to the first one, but the only difference is that we are using full propagators instead of the Bay propagators. So we have the same ansatz as before. So we have some kinetic part that is built by the omega squared, so the derivative term, and the effective mass, and then an interaction that is built from local sextic and quartic interaction and bilocal sextic interaction. But the difference is that we assume that in our diagrams, the Bayer propagator here is replaced by the full propagator, and that is actually the reason that we have this 1 plus u bar 2 factors in the denominator of our flow equations here. So the flow equations are almost similar to the perturbative ones. The only difference is this full propagator here that comes from the effective mass, basically, that we consider. There is also another diagram, which is this diagram here, that comes from this diagram. So the solid line are the full propagators between the bubbles. But other than that, it's the same structure. So the reason that we didn't have this in the perturbative one was that in the perturbative one we were in the small coupling regime. So we had this assumption that the couplings are small, and we only looked at diagrams that are built from one loop, two vertex diagrams, which would have removed that.
But this diagram, to which geography?
So this is this one. So we have U4 3. So this is U4.
Can you have more loops, more building blocks in this?
So you can't. So if you are using the full propagators, you can't have more loops because so we are in the So if you look at the Wetterich equation, in Wetterich equation we had this one loop structure, and what we do in each part for each equation is that we derive the Wetterich equation with respect to the field, to the mean field, basically the background field, and then we can generate loops in the Wetterich equation. But we have loops in the sense of the Bayer propagator. So if you have the full propagator, you can imagine you have the loops inside the field.
Yeah, I wanted to ask like this: can you have more vertices in this type of diagram? Like not, you said like before in perturbative case you had two vertices connected. Now you have three. Like so you have four and more if you do not restrict yourself to the small coupling limit.
No, I don't. You can try, but you can't construct anything beyond that. But because you only connect. So if I add another 4-point interaction, then I would get something that contributes to U8, not U6.
Like
of course you can. But
that you should consider U8.
Yeah, but we cut at U8. That's the general part, and then we see what we get, and then we move on to the next term. So that's what we mean. Actually, that's good that you asked that. It's a very good question because it brings us to the next part, which is, so what if that we are truncating too much? So we have different interactions that in our effective action that we are ignoring. But we are not going to higher points. We are actually breaking different symmetries in our next ansatz. So also we will discuss this later in the results, but now before that we introduce.
But which diagram corresponds to the U2?
So the U2 diagram is so it's U4. So the first term comes from dimensionless because we moved to dimensionless, and the second term comes from that. And you see we have two full propagators and the insertion which gives the pi and all the factors. So next we move to the so far we assume that the symmetries of the classical action were kept by the effective action, average action. Now we explicitly break them by choosing another ansatz. So we had this replica symmetry before in the classical action. That came from the fact that we didn't have any coupling of different replicas at the same time, and now we break it explicitly. So we modify our kinetic average effective action by so we have again the same terms as before, but we add this term that basically couples two replicas at two fields from two replicas at the same time, and we call Q the strength of the coupling of these replicas. And we also modify our interaction part. So again, we have this local part, which is the same as before. We modify it a bit too here. We'll see it later. We have this non-local part, which is exactly as before. But here we add this coupling replica. Again, 4-point. So this would be basically a 4-point interaction that couples different replicas at the same time. So M beta and M alpha at the same time. We do another breaking here that we assume that our background field M alpha has this structure. So we have sigma alpha. So we have a unit vector sigma. And rho alpha is square root of 2 rho alpha n is the length. So this is another breaking of the symmetry. And we also break the ON symmetry by developing around a non-zero vacuum instead of that we call kappa or square root of kappa. Instead of developing around the vacuum zero as before. So here, So here is another. Representation of the terms that we look at. So we have the bilocal sextic interaction as before, but here we have this replica coupling term. And we have V we choose V as the strength of the coupling. And I don't know if it's visible, but here we have blue dots on one side and red dots on the other side. So it shows that we are in the same bubble. So the bubble still represents the time index. So we are in this. So they are all in the same time. But the two on the right are evaluated at one replica, and the two on the left are evaluated at another replica. And they are dot multiplied with each other. So that means that the structure of the inverse propagator that we had before would change. So before we had an inverse propagator that was completely symmetric in all indices, replica, ON, and so on. But now we have everything possible. So we have a local term, so with conservation, with time translation symmetric, and one that breaks that. So, but we ignore B for now. and we look at A. But then again, if we look at A, there is a term that respects replica symmetry, delta alpha beta, and the ON symmetry, which comes from the terms that we actually didn't change, the local terms and the derivative terms. But there is another term that we add here that explicitly breaks the replica symmetry. So there is this parameter Q that we introduce in the 2-point function, 2-point interaction, and there is also the contribution from 37, which actually depends on the dot product of sigma alpha and sigma beta. So basically you can imagine how dependently the direction of each replica is with each other. So if they are connected with each other, then we would also break the replica. So if there is an alignment between different replica, then we would be also breaking the replica symmetry. And there is another D term that also breaks the ON symmetry, but for now we ignore it. Next, we show the results. So first result that we have are the results from the perturbative flow equations. So on the left, you can see the RG flow near the. So we only discuss the flow near the Gaussian fixed point for now. So you can see at the flow equations of the flow of U4 and U6, the local quartic and sexic interaction near the Gaussian point. So we start with a small value. On the left, without the presence of the disorder, so we put U6 tilde, the bilocal part, to 0 on the left. And as you can see, it is pretty regular, and it moves toward the fixed value at every scale. And at the right, you have the singularity that comes as if we if we have the small disorder, we add a small disorder, so a U6 tilde that is not equal to 0. You can see that the singularities appear in the flow of the equation, flow of the couplings. So in general, in renormalization groups, this appearance of the singularity are indicators that in our approximation we did something wrong, and that's why our approximation is breaking down. So the singularity, you can remember, is just some sort of indicator. You can see it as an indicator of breakdown of the approximation. There is also another caveat with the left-hand side. Although there are no singularities, but we know for a fact that we assume that the couplings are small in the perturbative regime. And it means that after some value, if they become too large, even this diagram is not valid anymore. Which brings us to the next part, the non-perturbative one, which we can, we don't need to limit the value of the couplings to a small, the couplings to a small value. So now you have on the left-hand side U2, so the effective mass, the flow of the effective mass, and on the flow of the local sexic interaction on the right. So we start with, again, a very small U6 tilde, the yellow diagram. And you can see as we increase U6 tilde, in the green and blue curve, singularities appear again. So it shows that the singularities that we had before were not an artifact of the perturbative approximation that we used before.
But that means on this diagram, so that you just put 0, U6, for example, equal 0, 1, so on this.
So I think it just gives us more or less the same thing.
Not on the diagrammatic way.
Oh, you mean the diagrammatic? So if you look at the flow diagrams, the flow equations, so here it would basically remove this term, and of course this term.
Just will be removed.
So we removed all the graphs that include the bilocal sextic interaction.
But what means zero? It's zero. So you just get zero at one.
So you mean here?
On next slide. Here, the U60 is equal 1.
So U60 is means that at the first step of our FRG. So we choose a K. It can be K0, for instance. So you can see it as K0. So because you see that we have here this minus log of K, the renormalization time, and if it's 0, it means that the K is equal to 1 basically. Fine. And next we move to the results that we got from breaking the symmetry explicitly. So you can see that again, if we are, there was this parameter Q that was basically breaking the symmetry, the replica symmetry explicitly in the kinetic part. And what we do, we increase it gradually. And what we observed was that again with the kappa is was the value of the vacuum that we expanded around, and U4 again the quartic interaction. And as we saw originally a singularity for the flow diagrams, but as we increase this Q that breaks the replica symmetry explicitly, we saw that it actually removed the singularity. So it looks like it's going up, but it stabilizes actually after a point. And we saw that actually this Q removed and regularized the theory. And now a very brief comparison that we with what we had from before. So we had in our previous work we looked at the a slightly different model. So this is the Hamiltonian of the model that we have. So we have a derivative term like before, and we have a potential that is exactly the same as before, but the disorder is also the same in the second term, but there is an additional matricial disorder that comes from this matrix Kij, and we assume that Kij is a symmetric matrix. And as you might know, in large n limit, the eigenvalues of the symmetric random tensors, random matrices would tend to a Wigner semicircle. And then what we did was we looked at this interaction term in Kij as some sort of additional dimension to our previous time dimension that we had. So you would see that the inverse, the propagator would look at something like omega squared plus some lambda, the eigenvalues of the matrix plus m squared, and then we interpret these lambdas as some sort of momentum, generalized momentum, after shifting it a bit. And then what we did was doing the same machinery of renormalization by integrating out the UV modes in that generalized momenta space. And we also observed the same thing. Oh, sorry, that was too much. So we observed the same effect that if we break the, so we saw singularities at first, and then we observed that if we break these singularities through some explicit term, they remove these singularities. And thank you very much for your attention.
Okay, the talk is open for questions and comments. I have a small question because you mentioned that you have multi-body interactions.
Yes.
Yeah.
Multi-local interactions.
Multi-local interactions. So you have no idea how do they look in the real space, or they are just on the spot?
I mean, on the space, so our space is just one-dimensional. So it's basically connecting different fields evaluated at different times with each other. So that's how it looks.
It's not that
but keep in mind that they are in different time, in different replicas. So you can imagine that there are different dimensions that we are.
So it's impossible to imagine in real space.
I don't think so. I mean, it's a mathematical. So
Okay. Yeah, okay. Any other comments or questions?
So you mentioned in the introduction that the work in general on spin glasses is interesting for the AI applications. So could you imagine any application of your results to this domain?
So actually not the main part, but the very end where we define this integrating out. It's actually a work in progress that we are working on. That so one thing that happens is that so if we look at this as an additional dimension, so it means that it's a special dimension that is that has a dimension, you know, the canonical dimension of the coupling that comes from that depends on the value of the cutoff that we have. So it's a cutoff dependent canonical dimension, which is pretty weird in normalization group literature. And what we look at is the value of the canonical dimension from a given matrix. So this matrix could be pure noise. So it would be like Wigner or Marchenko-Pester, or it could be plus some signal. And it turns out these canonical dimensions that change, that we can determine by looking at this Wigner matrix, would be different if we have a signal, for instance. So it could be used for signal detection.
Great, thank you.
Any other comments or questions? Okay, so we thank the speaker.